So here's a question that often comes up in biology labs, in microbiology labs, in chemistry labs where people are growing materials, and so you're asked to prepare a buffer of a particular pH. And so in this particular case we need a carbonate buffer of pH 10.00, and we're studying the effect of acid rain on limestone rich soils, and so this is all an issue of alkaline soils, and so we need a pH of 10. And so the question is, well, how many moles of sodium carbonate must be added to 1 litre of a freshly prepared solution, 0.20 molar solution of sodium bicarbonate? And we're going to make this buffer. And so the Ka of bicarbonate is 4.7 times 10 to the minus 11. Again, very small number. And so you might say, well, you know, what's the acid here? Well, if we look at sodium bicarbonate, if we take sodium bicarbonate and we put it in water, it will break apart, dissociate into sodium ions and also bicarbonate ions. And bicarbonate has this hydrogen here, so it can act as an acid, it can act as a proton donor. So this is the acid, and it comes from this salt which dissociates in water. So this is the acid. And typically, you know, the first thing you want to do is to write the equation for what's happening. So here's bicarbonate, which is acting as an acid. So this proton is going to get donated to the water molecule to indeed produce hydronium ion. And what's going to be left is the carbonate ion, CO3 2-. And you'll notice that bicarbonate has lost one of these hydrogens as a proton, and the difference between bicarbonate and carbonate is a proton. So this is an acid acting as an acid. This is the conjugate base of bicarbonate. And rather interestingly, if we want to make a buffer, we need a weak acid, in this case bicarbonate ion, and we need a conjugate base of that acid, and that would be carbonate. And so it just so happens, well, we need some source of carbonate, and so we could use sodium carbonate as a source, and indeed that is what the question is asking us to do. So this sodium carbonate will give us the conjugate base that we so desperately want. And so we could go about this using an ice table, or in this particular case we're given the value of Ka. We've been introduced to the Henderson-Hasselbalch equation, and we could say, well, we know that pH is equal to pKa of the acid plus the log completely of the conjugate base divided by the acid, the concentrations. So we need the value of pKa. Well, we know that pKa is minus log to the base 10 of Ka. We're given the value of Ka right up here, and so we can put this in the equation and we get a pKa of 10.33. So now what we can do is we can add in all the information that we know. Well, we know that pKa is 10.33, which is good here, plus the log of the conjugate base, which is carbonate, and so carbonate is coming from this sodium carbonate, which is what we actually want to know what the concentration is. The acid in this case is bicarbonate, and it came from 0.20 molar sodium bicarbonate. So this value here is 0.20 molar. And so here's where this 0.20 molar comes in. We know that the value of the pH that we want is 10.00. Sorry, missed out the zeros. And so what we can do is we can rearrange this. What I've basically done is I've subtracted 10.33 from each side, and then we take the anti-log here, and we can see that if we multiply both sides by 0.20, we end up with a concentration of carbonate that we need to add of 0.094 molar. And so this 0.094 molar carbonate is going to come from our sodium carbonate. And so we need 0.094 molar is the concentration. We're actually going to have that present in 1 litre of buffer. How do we know this? Because in the question it says how many moles must be added to 1 litre, and so this is the 1 litre we're talking about. We know the concentration of carbonate. We know the concentration of carbonate that we need, and so the concentration of this carbonate is in molar is going to be the number of moles of sodium carbonate divided by the litres, which is 1 litre in this particular case. And so if we multiply both sides by 1 litre, we see that the number of moles of sodium carbonate that we need is 0.094 moles of sodium carbonate. And so this would be our answer here. And just as a little bonus, because of course it's hard to weigh out moles, you know, in the good old days we could always convert moles to mass. So this is not specifically what this question is asking, but it's a little bonus. The mass of the sodium carbonate to add would be the number of moles, and then we would multiply it by the molar mass of sodium carbonate, which is 105.99 grams for every 1 mole of sodium carbonate. And we would end up with 9.96 grams. So if you were asked for the number of grams of sodium carbonate that you needed to add to the solution to make this buffer, this would be the answer, 9.96 grams. And so the fabulous thing is, now you could prepare a buffer of any pH. So if you were asked to prepare a buffer of pH 10 or a buffer of pH 4 or a buffer of pH 6, you could do this by using the Henderson-Hasselbalch equation.